Good evening, everyone. Welcome to week 8 lecture. Week 8 live session. Today we will discuss theory of Brownian dynamics. I will discuss few problems from this module of lecture where uh, we will discuss the theory of Brownian dynamics in detail. Let's start with the first problem. Problem number 1 is the equation of motion of a small particle undergoing Brownian motion. So to write down the equation of motion, we have to balance the force. So we have to write down the balance the force and write down an equation to uh, get the equation of motion. So for that, first we have to find out what are the forces acting on the particle. So force is given by, from Newton's second law, force is uh, m dv dt. Now this is force because we are considering a particle which is of constant mass. Constant mass. From the general statement of Newton's second law, the force is given by dp dt, rate of change of momentum. And if you write down p is equal to mv explicitly, this term will give you two terms, which is one of it is m dv dt and v dm dt. Now if the mass is constant, this term is 0. So in that case we are left with the first part only, which is basically more popularly known as mass times acceleration. But remember, force is mass times acceleration only when we are considering particle which is of constant mass. So if the particle mass is constant, in that case the left hand side of our equation is m dv dt, that is force. Now we have to find out what are the forces acting on the particle. So there will be two kind of force acting. One is because the particle is moving inside some kind of solution or some medium, maybe air or water or some other liquid or solution. So there will be a resistive force or the drag force, and we will denote this force as I into V. And now this is a safe assumption that this viscous drag or any resistive force that is proportional to velocity, directly proportional to velocity, which and xi is a constant, and xi depends on the nature of the particle, shape of the particle, and size of the particle, these things, and also the nature of the medium where the particle is moving. So for a spherical particle, this xi is given by 6 pi eta r, where eta is the coefficient of viscosity, and r is the radius of the particle if it is spherical. And only if the particle is spherical, then only we can safely assume that the force is given by 6 pi eta r v, which but if the shape of the particle is something else, like not spherical, it is some ellipsoid or some cube or some other shape, then this formula is not valid. This formula is only valid when the particle is spherical. Okay, so it's a special assumption. So in this case, while writing the equation of motion, we will not assume this spherical assumption, when we keep the resistive force or drag force due to viscosity, due to visco or viscous drag, as xi into v. We will keep this term as general. So that is one of the force acting on the particle, and there will be another force acting on the particle, which is due to the thermal motion of the medium itself. Medium, if it is a solution, the solution particle itself. So this particle we are considering, that is very small. Particle is small, and there will be non-zero temperature in the medium. So due to non-zero temperature, there will be thermal energy associated with all the medium particle, which is basically the kVt. Due to that thermal energy, because it is not absolute zero temperature, there will be small vibration with the small vibration in the particles, in the medium particles, and due to that small vibration, it will randomly hit the particle we are considering. We are writing the equation motion. Uh, it will hit the particle from random direction and give some random kicks. So there will be a random force acting on the particle due to the thermal fluctuation of the medium. So the random force we will write as random force, we will write as f of r t. So these are the two forces acting on the particle. So the equation of motion becomes m dv dt, mass time acceleration, is equal to minus xi v plus the random force f of r. Now there is a minus sign in front of xi v because it is always acting opposite to the direction of velocity. So if I am trying to move along the positive x direction, the viscous drag or whatever drag in the medium, that will act in the negative x direction. It will try to stop me. So there is a minus sign. And FRT is a random force, which is there are a special scenario where we can model this random force by using some assumption, but this is really a random force, and the particle is getting thermal kicks from every direction, so every direction is equally likely. So FRT is a completely random force. And now this xi into v, this so this force has two parts. One is resistive and one is random force. The random force is more important when the particle mass itself is very small. So in that case, the random kicks will be more effective. Uh, if the particle mass is like less than a milligram, or it is something like a pollen grain or some fly ash or some dust particle or something like that, in that case random force, the thermal kicks are more effective compared to the drag force. But if it is a large particle, suppose it is an iron ball or something, in that case the medium thermal kicks are not very uh, very much affecting the motion of the particle. In that case, the viscous drag, due to the bulk, big size of the particle, the viscous drag is more. Uh, so in that case, so there is two regime. Like in one regime, the viscous drag force, resistive force, those are more important. Thermal kicks are not affecting much. But if there is another scenario where if the particle is very small, something like dust particle or some pollen grain, in that case the thermal kicks are more important. So this is our desired equation of motion. Brownian motion. So yeah, so this is the equation of motion. Now there can be another question, which is a true false type question, that true false type question, that Brownian motion theory relates microscopic fluctuation, microscopic fluctuations to macroscopic response of the system, of the system to external forces. Now, if you see that in the above equation, the FRT is the microscopic fluctuation in the system, and we are equating to MdVdt, which is the macroscopic response, overall response of the system to the external force. So indeed this is a true statement, and the theory of Brownian motion actually relates the microscopic fluctuation to the macroscopic response of the system. So this statement is true. Okay. Okay, let us move to next question now. Question number 3. The mean square displacement, the mean square displacement of diffusive particle is given by which relation? So let me short write down the option. There is 2 dt. So this is diffusive mean square displacement in 3D. 2 dt, 4 dt, 6 dt, 8 dt. Right. So from our discussion on random walk and the early discussion on the random walk and diffusion, from that we know already that for a diffusive particle, x square average goes like t, proportional to t, whereas for a ballistic particle, x square average is proportional to t square. So in that scenario, it is, suppose some particle moving in constant velocity, x is dt, so x square average has to be proportional to t square in that scenario. So there is, in more general way, we can write more generally that x square average is proportional to t to the power nu, some nu. Now if nu is equal to 0, that is the trivial case, static particle, not at all moving, particle is not at all moving. So if nu is less than 1, in that case it is subdiffusive, slower than the diffusion, subdiffusion. If nu is equal to 1, then it is perfectly diffusion. If nu is greater than 1, then it is super diffusion, which is faster than the diffusion, super diffusion. And if nu is equal to 2, in that case it is ballistic, something like particle moving in a constant velocity. So this is the full regime of x square average. Depending on the exponent of the x square average, exponent of time, we can characterize the motion of the particle into this kind of diffusion. So in our question for diffusive particle, it is no doubt that x square is goes like t. Now we have to find out the constant in front of this. So it appears like x square average is given by relation 2d into t. So the capital D here is diffusion constant, and the small d is the dimension. So indeed x square average is 6 times dt in 3D. Okay. So similarly, if you want in 1D, you have to put only d is equal to 1. So in that case, we get our old result, x square is 2 dt. In 2D, it is 4 dt, and in 3 dimension, it is 6 dt. But only if the motion is diffusive. In any other kind of motion, this exponent of time will change. The value of nu will change depending on the nature of the motion. Okay. So in this case, the correct option should be 60T. So next question, question number 4. Question number 4 is this: origin of time is not important. Time is not important. So this is which kind of symmetry or invariance gives this kind of property. So if you remember our correlation function uh, C t t prime is only dependent on it's a function of t minus t prime. So this is also equivalent to saying like t minus t prime 0. So it only depends on the difference of times between 2 points. So if I want to calculate the correlation between time point t and time point t prime, it will only depend on t minus t prime, the time difference between the two time points. So if instead of that, if we calculate t is equal to 0 and some time which is t minus t prime, it will give exactly similar result. So where we are fixing our origin of the time t is equal to 0 point, our starting point, when we are starting the time axis, that point is not important. We can keep our time origin anywhere, but it doesn't depend on the correlation function doesn't depend on that origin. It is only dependent on this difference between the two time points t minus t prime. So this kind of property is called as time transition symmetry, where we can transit the origin to any point, but depending on the position of the origin, the property of the function is not dependent. It is only dependent on the difference between the two time points t minus t prime. Similarly, so this is time translational invariance. Similarly, if you have a movie, suppose you are recording motion of the particles inside the box, and if you play that motion in the reverse order, and if it is completely if it is not possible to distinguish between two video, whether it is playing in the forward direction or in the reverse direction, then it is called time reversal symmetry. So if you allow to run the time in the reverse direction, backward direction, you will not be able to tell that it is going in the forward direction or backward direction. It is completely indistinguishable. So in that case, time reversal symmetry is present in the system. So it doesn't depend in which direction of you are, whether you are looking at the video from the positive time axis, along the positive time axis, or you are going along the negative time axis. Okay. Now, next question is question number 5. The ensemble average of random force term in the Langevin equation. Ensemble average of random force in Langevin equation. So as we have already told that this random force is generated due to the thermal kicks of the particles, medium particles or solid particles, or if it is in the air, by the air molecules, or if it is in the water, by the water molecules, the random force, random thermal kicks given by the, so you can imagine that it is equally likely to get a thermal kick from every direction. So there is no preferred direction. So this is our particle, suppose, and these are the air molecules or solvent molecules. So it is equally likely that it will get a thermal kick or a random force, which we are talking about, from any possible direction. So there is no preferred direction. From any possible direction it can get a kick. So if I am looking on many ensemble, very large number of the order of say 10 to the power 6 or 10 to the power 7 number of ensemble, so we will see that in each ensemble it is hitting the particle is getting thermal kicks from different direction. And if I consider a large number of ensemble, I will see from all possible direction it is getting a thermal kick. So if I take an average of all those forces, it will be equally likely to each direction. So the ensemble average will go to 0. So that's why the FRT ensemble average, this is 0, because from every direction I can get a force. So the resultant force after summing over all possible direction, this will be a 0. Okay, but the point to remember here that in case of, even though the average is 0, the square average, this quantity is not. Move to next question. And next question is, so the nature of velocity with time for a large metal ball falling in a liquid. So in this case we have to start with equation of motion first. So as we have written in the case of Brownian dynamics, in this case also we will write mass into 4, because it is a large metal ball, so mass is a constant quantity in this case. So we will write the force is equal to mass time acceleration, that is mdv dt. Now this is equal to minus xi v, and there will be no random force because it is large metal ball, so it's a massive of the order of kilogram or gram maybe. So in that case these thermal kicks are not that important. So in this case the viscous force is the only important factor here. So first we will consider that there is gravity and there is no gravity, uh, only the viscous drag is acting on this particle. So in this case the particle, from the our common idea, we can say that if I am throwing some particle inside a very viscous medium and there is no gravity acting, so whatever the initial velocity I am giving to the particle, due to the resistive force of the medium, that velocity will die down to 0 and particle will come to rest. So that's our common idea. So if I now take dv by v to this side will be xi by m dt. So we'll call xi by m as k, xi by m is k. So in this case, if I now integrate both sides, xi by m is k, so this is k and 0 to t, and this is v0 to v after time t. So this side will be log of v, limits are v0 and v, and this side is minus kt. So this will be ln of v by v0 is minus kt. So v by v0 is e to the power minus kt, and from this v is v0 e to the power minus kt. So now you can see, if you wait for long enough time, so the initial velocity is v0. V0 is the initial velocity. So this is the initial velocity, and if I wait long enough time, this e to the power kt function looks like something like. So if I plot now velocity versus time, this is velocity, this is time, it will be some function which is exponentially decay, something like this. So it is starting from this point, t is equal to 0, suppose this is v0, and it is going to 0 after some but we have to wait long time to see actually 0 velocity. It will exponentially decay to very low value, but actual 0 will happen only at t tending to infinity, the v is 0. Now in this case we haven't considered that particle is large and it has mass, but the actual scenario that if I write down all the forces, m dv dt is mg, which is, so suppose the particle is moving under gravity, so m dv dt, v is downwards towards the ground, mg is also acting downwards, so both of them are positive, but opposite to the motion of this gravitation, due to this gravitational force there will be a drag force, resistive force, so it will be minus iv. Now the situation is slightly more complicated here. Let us first do a division with m, so it will be g minus xi by m is our k, g minus kb. So this is our equation. Now do dv by g minus kb equal to our dt. Now this will be, let us multiply by minus k both side. Now if I want to integrate this side and this side, let us integrate this side with, from velocity v0 to v, this side from time 0 to t dt. So this side will be a logarithmic function again, log of g minus kv with the integration limit v0 to v, and this side will be minus kt. Now if I put v and v0 integration limit, it will be ln of g minus kv by g minus kv0, which is equal to minus kt, and again g minus kv by g minus kv0, this will be to the power minus kt. And now if you do some simplification here, you will get again some kind of exponential decay of the velocity, but there will be a scenario when the force due to gravity and the viscous drag will be exactly equal. So from this you can write what is v as a function of, in terms of v as a function of time, you can write down, there will be terms like e to the power minus kt and etc., but that requires a little bit simplification. So you can write this upper hand side as g minus kv0 plus kv0 minus kv, and there will be then divide by this term, so there will be cancellation. But even from here, the first equation, you can write m dv dt, m dv dt is equal to mg minus psi v, but when viscous drag is exactly equal to the gravity, in that case V is equal to mg by, so let me write down mg by psi or g by k. So this is our velocity, which is terminal velocity. So what happens if I am throwing a particle with some velocity, initial velocity, in a medium which is very viscous? There will be viscous drag and there will be gravity acting on that. And after some time there will be a scenario when the viscous drag will exactly balance out the force due to the gravity, and there will be no force acting on the particle, so there won't be any acceleration or deceleration. So particle will reach a velocity which is completely constant, and that constant velocity is called the terminal velocity. So in this scenario, this terminal velocity is mg by psi, or g by k. In terms of our definition, k is psi by m. So k is psi by m. Okay. But remember that as we are discussing here a motion of a very large particle which has a mass of gram or kilogram order, in that case the random force due to the particle in the medium or in the solution that is not important in that case. So this is in contrary to the theory of Brownian dynamics or Brownian motion. This is some kind of a motion which is a massive particle inside a viscous medium. There is no Brownian motion at all, random motion associated with this. There are forces acting on the particle due to thermal kicks, but because the particle is very massive, in that scenario, the random forces from the solvent particles or solid particles, those things are not very important, affecting much the motion of the particle. Okay, so let us move to next question. This was question number 6. Let us go to question number 7. The random force the random force is to model which of these? In the Brownian dynamics, this random force is to model which of these? It will capture the effect of which of these? Like, so the motion due to thermal kick, or it will, so let me write down, this is like solute solvent collisions, effect of solute size, or it is unknown, something like it, some other options. But the, as we have discussed multiple times, that random force is due to the thermal kicks between solute and solvents. So if I am looking to motion of the particles inside the solution, this will essentially capture the interaction of solute solvent collision. So there will be collision due to the thermal kicks between the solute and solvent. The random force is to model that collision. There is no connection with solute size or other things. So this is the most appropriate option in this case. So 8 is at equilibrium velocity of particle is, so there are multiple options, say V is equal to root over kt by m, V is equal to kt by m, K is Boltzmann's constant, T is time, T is temperature, and m is the mass of the particle, or V is kt by m whole square, or V is m by kt. So which is the correct option? So even though without looking at anything, you can from the dimensional analysis you can calculate that which is the correct option in this scenario. So suppose the kt is something like energy, right? Kt is energy, so it has a dimension with force, so it is same as work done, so force into displacement, so it will be like m L square t to the power minus 2, something like this, right? Now if you want to get a dimension of velocity, there should be something like energy by mass to the power half. Now if you calculate m L square e to the power minus 2 by m to the power half, this will give you L to the power minus 1, which is the dimension of velocity. So if you from immediately from this calculation, dimension analysis kind of calculation, you can tell that this is the correct option. In other option, the dimension is not of the velocity, something else. So but why this happens? So at equilibrium, so what is the connection with equilibrium? At equilibrium, the equipartition of energy holds. So half mv square will be half kt, and v will be kt by m. So each degree of freedom will get some temperature energy, thermal energy, which is equivalent to half kt. So from that equation, the kinetic energy will be equal to that energy. From that equation, we can calculate what is the velocity at equilibrium only, because equipartition theorem is only valid at equilibrium. So at equilibrium, from equipartition of energy, we can get this relation. So from dimensional analysis, you can calculate which is the correct option. But if there is some other option like v is equal to root over 2 kt by m, in that scenario, you have to know this idea that at equipartition, due to equipartition of energy, each degree of freedom of the particle will get energy, thermal energy associated, which is half kt. So next question, question number 9. So the random force, this is again a true false type question, true or false. The random force is determined by motion of thermal motion, thermal motion of fluid molecules, and will not be affected by the potential U of x acting on the particle, acting on the particle. Whether it is true statement or false statement, we have to analyze. Now, if I want to write down again, let us write down the equation of motion. So m dv dt, the force is equal to, we have already done xi v plus f of rt. So xi v is due to some viscous drag and frt is the random force. Now, on top of this, if there is some force acting on the particle which is due to some potential, suppose it is moving on a potential which is simple harmonic type or something like that, so in that case there will be an extra term force acting on the particle which is something like minus del u del x. If ux, potential form of the potential, is known to us, force will be minus del u del x. So from that we can calculate what is the force acting on the particle due to the potential itself. But this if rt, this is not dependent on that potential. So del u del x minus del u del x give you a force. So if we want to write down the full equation, suppose, so dv dt is like double derivative of position, mx double dot is equal to minus I x dot minus del u del x, where ux is the potential and there will be a force due to that potential. Now if we think about this FRT is the random force due to thermal motion of the fluid particles, and this is the force acting on the particle due to the external potential. So suppose Ux can be an electric field or something like that. So if I place the whole chamber inside some electric field, so there will be force due to the electric field on the particles if these particles are charged particles. So again, this random force is completely independent, which is due to the thermal motion of the fluid particles, and this del u del x, this is due to some external potential, electric field or magnetic field or something like that, maybe gravitational force, something like that. So that thing is not affected by the thermal peak, is not affected by that potential. So similarly, in the previous problem where we are writing down the equation mg, this mg is a force which is due to some external potential. So potential is something like mgx minus mgx maybe, and if you take minus del u del x, you will get force mg, which we have written down here. But that mg, external force, again in this case there was no random force because particle itself is massive, so there is no effect of random force, no point in considering that force explicitly again here. But if there are, the motion of the particle is size of the particle is very small, in that scenario the random force and the external force both are important, and both of effect of them, both of them will be independent of each other. There is no connection between the random force and the external potential. Okay, so any doubt here? So just like this, if we are considering the size, mass of the particle or size of the particle, how that thing is important, you can consider calculation, small calculation like this, that raw water is 1 gram per cc, and suppose you are considering the motion of a particle which is 1 gram or 10 to the power minus 3 kg, and you can consider another particle which is like 10 to the power minus 12 kg. Now if you calculate the velocity of these two particles at same temperature, if you calculate that velocity of this particle two different again, you will see in one case you will get a velocity which is very small, like 1 nanometer per second or something like that, which is negligible for this kind of massive object. But in this case you will get 10 micrometer per second, which is considerable in this size of particle. So if the velocity is not that important in those scenarios, we'll ignore the thermal uh, the motion due to the thermal kicks, or the motion due to the random force uh, appearing from the fluid molecules inside the solution. Okay. Yeah, so how did we calculate the velocity in that scenario? You have to calculate, so we know that v is root over kVt by m. So kb is 10 to the power minus 23 joule Kelvin, and t is 300 Kelvin, something like this. And m, you have to put two different m here, this one, this one. From that you can get velocity for two different cases. Suppose this is m1, this is m2, v1 and v2 you will get. So under so this is some room temperature condition. 27 degrees centigrade or something like that. In room temperature condition, you can calculate what is the velocity associated. So v1 will be almost negligible because it is a particle of mass of the order of grams, but this is very small particle m2. In that sense, you will get some velocity which is considerably large. Okay. Any question at this stage? Okay, if not, we can stop here today. We have discussed some problems from Brownian, the module of Brownian dynamics, and next week we'll move on to some another section. Okay, good luck.